So today's lecture we'll be seeing the concept of the discrete Fourier transforms, and these are the two references: the book by Troakis and the second book by Manolakis, where the first book will be the main textbook for the full course, almost the full course. Now we'll see what is discrete Fourier transforms. So in the last semester you would have learned something called discrete time Fourier transforms. Discrete time Fourier transforms. That is the Fourier transform of a discrete signal. Now what does a Fourier transform do? So that converts a time domain. This is a transformation that converts a discrete time signal, that is discrete time signal in the time domain, that is a signal like this n and x of n, and discrete signal, an example will be something like this. Is just an example, so it will have, so this n, unlike in the time domain where in the continuous case n will be equal to t, that is time, but in the discrete case n is equal to the sample number. So n is always an element of integer values, that is it is always an integer value, that is n takes only integer values. So that is something that you need to understand, that is n is not the time but the sample number in the case of a discrete signal. So now what I'll do is I'll pass this signal through a transformer, that is a discrete time Fourier transformer. So what does it do? So what you will get is a graph like this. Where note this point, that is the x-axis now is, instead of n, it is changed to omega. Omega is the frequency of the signal. So that is we are getting. So what DTFT does is it converts the time domain, discrete time domain signal into the frequency domain. So we get a signal like this. After passing this signal through a discrete time Fourier transformer, we get a signal like this, or a waveform like this. So something that you need to note is that in the case of a, even in the case of a discrete time signal, when you take the DTFT, the waveform that you are going to get as the output will be continuous in nature. That is something, a waveform like this. Now there's a speciality of discrete time signals, that is discrete time spectrum. This is known as the spectrum of the signal, that is the graph between frequency and amplitude is known as spectrum of the signal, and it is continuous in nature. Another speciality for the discrete time signal like this, the spectrum is going to be periodic in nature, that is it doesn't stop here, it again repeats, that is it again repeats, again it repeats both sides. So one thing that you need to remember is always you need to just consider, and also the periodicity of the signal is 0 to 2 pi, that is period is 2 pi, that is after this the same thing is going to be repeated for 4 pi minus 2 pi, etc. So another important point is discrete time signal spectrum is periodic with a period of 2 pi. So now onwards, for the full DSP course, you need to only bother about the range of 2 pi. That is, either you can take the spectrum in the range of usually minus pi to pi, or you can just worry about the frequency content in the frequency of range of 0 to 2 pi. Either this or either this would be fine. So for the full DSP course, we don't have to worry about what is lying after 2 pi or before 0, or if you are taking minus pi to pi range, you don't have to worry about any frequency content after pi or minus pi, because it keeps on repeating. So that is the speciality of the spectrum of a discrete time signal. Now let us consider the spectrum here, that is x of omega. This is DTFT. The dark line is the DTFT. But problem is that DTFT cannot be processed by a computer. Why is that so? Now, as I told you, this is a continuous signal, this x of omega, and there are infinite number of points for a continuous waveform. So it cannot be processed because of memory constraints, etc. It cannot be processed. So what is being done in order to process by a computer is that after getting x of omega, this waveform, this dark line waveform, after getting that waveform, what is being done is it is going to be sampled. That is, we have already learned sampling in the time domain previously. That is how a continuous time signal is converted to a discrete time signal. But here what is going to be done is, given a discrete time signal, first we convert it into discrete time Fourier transform. That is, take the DTFT and you get a waveform which is going to be continuous in nature. After that, I told you that it is periodic with 0 to 2 pi. That is a range of 2 pi. Either minus pi to pi we can take, or 0 to 2 pi range. And we don't have to bother about any other range. So look at this waveform, this dark line waveform. So in order for the computer to process, we will be sampling this in the frequency domain. That is, sampling in the frequency domain will give you the DTFT samples. That is just a sampled version of, so DTFT is basically sampled version of, that is DFT is just the sampled version of DTFT. So only this much is the basic concept of DFT. So these samples, the samples gives you the DTFT of the signal. And look here, we have only taken the range between 0 to 2 pi, or else I could have taken range between minus pi to pi also. That is also fine. Any way you can take. So I have taken the samples between 0 to 2 pi. So next, let us consider that we are sampling it for a, this waveform is sampled for delta omega. That is the duration between each sample is delta of omega, as we can see here. So now let us take n number of samples. That is, n samples are taken between 0 to 2 pi. N samples between 0 to 2 pi we are taking, and this distance between consecutive samples is equal to delta of omega. So now what will be delta of omega then? If you are having n samples between 0 to 2 pi, it will be shown here, delta of omega is equal to total range is 2 pi, out of which we are taking n samples. So that will be, so delta omega will be equal to 2 pi by n. So similar, so the kth sample, that is this sample, will be k times delta of omega. So the kth sample will be equal to delta omega into k, or 2 pi by n into k. Now we know the expression for DTFT, that is x of omega is equal to this particular expression. And our aim is now, as I told you, find out the expression for DFT. So expression for DFT can be found out by just sampling this particular expression. That is, let us find the kth sample of this particular function, this continuous frequency function. So what we have done is, the kth sample, we know that kth sample is at the point 2 pi k by n. So all I did is, instead of omega, I substituted omega is equal to 2 pi k by n. That is, I substituted it here, and I will get this particular expression. And what is the meaning of this k equal to 0 to n minus 1? That is because we have taken n number of samples. That is, this is the kth sample. So k can vary from 0th sample to n minus 1. That is, total of n samples are taken in the frequency domain in the range of 0 to 2 pi. That is what is this particular expression. K is equal to 0 to n minus 1. Now, so look at this part. This is n equal to minus infinity to infinity. Now consider a signal like this, x of n, that is a finite duration signal. In that case, what will happen? A signal of this form. This is just an example, a finite duration signal. It will be something like this: 1, 2, 1, 3. So that is a signal of length 4. Length 4 signal. That is a finite duration. That is the meaning of a finite duration signal, instead of the signal going from minus infinity to infinity. So a signal like this. So general case, let us assume that the duration is equal to L. That is, x of n has a duration of L. So now what we can do is, we can modify the expression, above expression 1.2. We'll modify it. That is, we just changed n equal to 0 to L minus 1, the same thing. Now we have to think about something more. That is, there is something called time domain aliasing. That is, we previously in the signal processing class, you would have learned about frequency domain aliasing. That is, overlapping in the frequency domain. That is, when a signal is sampled in time domain and reconstructed, you are going to get something. If you don't sample it at a particular rate, that is at the Nyquist rate, you will get some issues. That is overlapping in the spectrum. That is for time domain. So in frequency domain, you are now in the, this is DFT is actually sampling in the frequency domain. So when signal is sampled in the frequency domain, and then we are trying to reconstruct the signal. That is, after sampling in the frequency domain, if we are trying to reconstruct the signal, what will happen? That is actually trying to get the original x of omega from the sampled version of x of omega. There is an issue. That is, if you don't select n greater than or equal to L, that is, L is what? Length of the actual signal, x of n, and n is the FFT or DFT length. That is number of samples we need to take in the frequency domain. So we must always ensure that n is greater than or equal to L. This is an important point. So what is being done is, there is concept of zero padding. So now let us assume that a question is asked, like find the 8-point DFT of a signal. This is just an example of the previous case: 1, 2, 1, 3. So that is a signal length. That is, this is the first sample, second sample, third sample, fourth sample of signal x of n. But the question is, find out 8-point DFT. That is, n equal to 8, and what is L? L is equal to 4, because we only have 4 samples. So how do we do that? So there's a concept called zero padding. And always we need to remember n should be greater than or equal to L for a proper reconstruction of the DTFT. That is from the DFT. If you are reconstructing DTFT, if you want to get a proper reconstruction, you always have to ensure n is greater than or equal to L. So when such a question is asked, what will you do? The first step is you have to modify it. That is, you have to zero pad. That is, add zeros to the end so that you have to make the signal length L should be equal to, at least equal to 8. So that is, you add 4 zeros. So this concept is known as zero padding. So now, so when zero padding is done, n will be equal to L and the issue is resolved. And then you can directly apply the expression for DFT, that is this particular expression. So when n is equal to L, what you can do? You can modify the expression to this particular expression. That is, instead of x of omega, I just wrote it, just renaming x of omega k as x of k. That is the kth sample of DTFT. And instead of L minus 1 here, since I have 0 padded, it will be 0 to n minus 1, k equal to 0 to n minus 1. And similarly, if you want to get given x of k, if you want to get x of n, what you do is inverse Fourier transform. That is inverse discrete Fourier transform. So that is this particular expression. That is just taking it to the other side. And you will get a similar equation like this. Here also note this. N equal to 0 to n minus 1. Even though we know that the actual signal length is equal to 4 in this case, or L in general, we have to find out 0 to n minus 1 because we have actually calculated the signal for length of n because of zero padding. So this is the expression for inverse discrete Fourier transform, while this is the expression for discrete Fourier transform. So the basic concept that we learned today is discrete Fourier transform is the sampled version of discrete time Fourier transform. So this is all that is to be understood. That is basic of DFT. So that is all for today, and thank you.